Welcome to the definitive guide to the Thevenin's theorem. Let me show you a problem that every electrical engineering student faces. Here's a circuit. It's got voltage sources, current sources, 5 resistors, multiple loops. Now here's your assignment. Find the current through this load resistor, RL. Okay, you grab your pencil, you write KVL equations, maybe some nodal analysis, you solve a system of equations and boom, you get your answer. 10 milliamps. Great job, but wait, your professor says, now find the current if RL is 2 kiloohms instead of 1 kiloohm. So you start over. New equations, new algebra, new answer. Then your professor says, now try 3 kiloohms, now 4, now 5. You realize you're solving the same circuit over and over again, just changing one resistor. There has to be a better way. Enter the Thevenin's theorem. This is one of the most powerful tools in all of circuit analysis. Here's the promise. Any linear circuit, no matter how complex, no matter how many sources or resistors, can be reduced to just two components, a single voltage source and a single resistor. That's it. We call this the Thevenin Equivalent Circuit. And here's the magic. From the perspective of your load resistor, this simple circuit behaves exactly like the original. Same voltage, same current, identical. So instead of solving that monster circuit 5 times, you solve it once to find your Thevenin equivalent. Then, changing the load becomes trivial. Plug and play. Before we jump into calculations, we need to understand what the Thevenin's theorem actually says. Imagine I hand you a sealed black box with just two terminals sticking out. You can't see inside. You don't know if there are two components or 200. All you can do is connect something to these terminals and measure. Here's the key insight. From the outside, any linear circuit with resistors and sources will behave exactly like a simple voltage source in series with a resistor. Think about it. If I give you a mystery box and you measure the voltage across the terminals with nothing connected, you get some voltage. That's Thevenin, the open circuit voltage. Now, if you connect a resistor and measure current, you'll notice the voltage drops a little bit. Why? Because there's internal resistance inside fighting your current flow. That's Thevenin. From outside the box, you cannot tell the difference between the original circuit and the Thevenin equivalent. They are electrically identical at those two terminals. So, a Thevenin equivalent has exactly two parameters. Let's define them precisely. Parameter 1, Thevenin, the Thevenin voltage. This is the voltage you measure across the terminals when nothing is connected. We call this the open circuit voltage, VOC. Thevenin equals V open circuit. This represents the maximum voltage the circuit can provide. It's the push available. Parameter 2, Thevenin, the Thevenin resistance. This is the equivalent resistance looking into the circuit from the terminals, with all independent sources turned off. Alternatively, it's the ratio of open circuit voltage to short circuit current. Thevenin equals VOC divided by ISC. This represents the internal resistance, the opposition to current flow. All right, let's get practical. How do we actually find the Thevenin equivalent of a circuit? There are 4 clear steps. I'll break them down one at a time. Today, we'll focus on finding Thevenin. In the next section, we'll tackle Thevenin. Here are the steps for Thevenin. Step 1. Identify the terminals. Where are we finding the equivalent circuit? These are usually labeled A and B, or they're where the load connects. Step 2. Remove the load. Disconnect whatever is connected between those terminals. Now the terminals are open. Step 3. Calculate the open circuit voltage, VOC, across those terminals. Use any circuit analysis method you know. Voltage dividers, KVL, nodal analysis, whatever works. Step 4. Thevenin equals VOC. That's it. The Thevenin voltage is simply the open circuit voltage. Let me show you with an example. Here's a circuit with a 12-volt source, a 4 kiloohm resistor, R1, and a 2 kiloohm resistor, R2, connected in series. There's a load resistor, RL, connected across R2. We want the Thevenin equivalent as seen by RL. Step 1. The terminals are the 2 points where RL connects. Let's call them A and B. Terminal A is the top of R2 and terminal B is ground. Step 2. Remove RL. Now we have an open circuit between A and B. Step 3. Find VOC, the voltage from A to B. Since RL is removed, no current flows through R2 to ground, so the circuit is just R1 and R2 in series across 12 volts. This is a simple voltage divider. VOC equals 12 volts times R2 divided by R1 plus R2. VOC equals 12 times 2K divided by 4K plus 2K. VOC equals 12 times 2 divided by 6. VOC equals 4 volt. Step 4. Thevenin equals 4 volts. Done. Thevenin is the equivalent resistance of the circuit as seen from the terminals. Imagine you're standing at the terminals looking into the circuit. If you could measure resistance, what would you see? That's Thevenin. But here's the catch. You can't just measure resistance while sources are active. A voltage source will short your meter. A current source will send your reading to infinity. So we have to turn off all independent sources first. Then we calculate the equivalent resistance. Let's start with the simple case, circuits with only independent sources and resistors, no dependent sources. Here's the procedure. Step 1. Remove the load resistor just like we did for Thevenin. Step 2. Kill all independent sources. What does this mean? Voltage sources become short circuits. Replace them with a wire. Why? Because a perfect voltage source has zero resistance, so when it's off, it's just a 0-ohm wire. Current sources become open circuits. Remove them completely. Why? Because a perfect current source has infinite resistance, so when it's off, it's like an open wire. Step 3. Calculate the equivalent resistance between terminals A and B. Use series and parallel resistor rules. Step 4. Thevenin equals R equivalent. Done. Let's use the same circuit from before. 12-volt source, R1 equals 4 kiloohms, R2 equals 2 kiloohms. All right, let's put everything together with a complete example. Here's the circuit. We have a 24-volt DC voltage source on the left. Connected to it is a 3 kiloohm resistor, R1. From that node, two branches split. One branch has a 6 kiloohm resistor, R2, going to ground. The other branch has a 2 kiloohm resistor, R3, connected to a node, and from there, a load resistor, RL, connects to ground. Our goal, find the Thevenin equivalent circuit as seen by RL. Then we'll verify it by calculating the current through RL using both the original circuit and the Thevenin equivalent. They should match. Let's do this. Step 1. Identify the terminals. Terminal A is the top of RL. Terminal B is ground. Step 2. Remove RL. Now terminals A and B are open. Step 3. Find VOC, the voltage at terminal A with respect to ground. Let's use nodal analysis. With RL removed, we have one non-reference node, the junction between R1, R2, and R3. Let's call its voltage V1. Wait, actually, let me simplify. Since RL is removed, no current flows through R3, so the voltage at terminal A is the same as V1. V1 is determined by the voltage divider formed by R1 and R2. V1 equals 24 volts times R2 divided by R1 plus R2. V1 equals 24 times 6K divided by 3K plus 6K. V1 equals 24 times 6 divided by 9. V1 equals 16 volts. But wait, we need the voltage at terminal A. Since no current flows through R3, there's no voltage drop across it. So VA equals V1 equals 16 volts. Step 4, Thevenin equals 16 volts. Now for Thevenin. Step 1, remove RL. Already done. Step 2, kill the 24-volt source. Replace it with a short circuit. Step 3, find the equivalent resistance from terminal A to ground. Let's look at the circuit. We have R1 in parallel with R2 because the left side is shorted to ground. That combination is in series with R3. First, parallel combination. R1 parallel R2 equals 3K times 6K divided by 3K plus 6K equals 18K divided by 9K equals 2 kiloohms. Now add R3 in series. 2K plus 2K equals 4 kiloohms. Step 4. R Thevenin equals 4K. So the Thevenin equivalent is a 16-volt source in series with a 4 kiloohm resistor. Alright, let's tackle the advanced topic that separates beginners from masters: dependent sources. First, what is a dependent source? A dependent source is a voltage or current source whose value depends on a voltage or current elsewhere in the circuit. For example, a current source that outputs 2 times Ix, where Ix is the current through some resistor. Here's the critical rule: you cannot turn off dependent sources when finding R Thevenin. Why? Because if you remove the dependent source, you break the dependency and the circuit behavior changes completely. The Thevenin equivalent would be wrong. So for circuits with dependent sources, we use the test source method. Here's how it works. Step 1. Remove the load. Step 2. Kill all independent sources only. Short voltage sources, open current sources, but leave dependent sources alone. Step 3. Apply a test source at the terminal. You have two options: apply a 1-volt test voltage and calculate the resulting current I. Then R Thevenin equals 1 divided by I. Or apply a 1 amp test current and calculate the resulting voltage V. Then R Thevenin equals V divided by 1, which is just V. Use whichever makes the math easier. Step 4. Solve the circuit using KVL, KCL, or nodal analysis to find I or V. Step 5. Calculate R Thevenin equals V divided by I. Let's do an example. Here's a circuit with a 12-volt source, a 3 kiloohm resistor R1, a 6 kiloohm resistor R2, and a dependent current source. The current source outputs 2 times Ix, where Ix is the current through R1. We want the Thevenin equivalent across RL. Finding V Thevenin. Remove RL, find VOC. I'll spare you the details, but using KCL and Ohm's law, V Thevenin equals 8 volts. Finding R Thevenin. Remove RL. Kill the 12-volt source, short it. Keep the dependent source active. Apply a 1-volt test voltage across terminals A and B. Analyze the circuit. Let's call the current flowing out of the test source I test. We need to find it. The voltage across R2 is 1 volt, same as test voltage. So current through R2 is 1V divided by 6K equals 1 over 6 milliamps. Now the dependent source outputs 2 times Ix. We need to find Ix. Using KCL at the node and working through the algebra, Ix equals 1 over 9 milliamps. So the dependent source outputs 2 times 1 over 9 equals 2 over 9 milliamps. By KCL at terminal A, I test equals current through R2 plus current from dependent source. I test equals 1 over 6 plus 2 over 9. Common denominator. 3 over 18 plus 4 over 18 equals 7 over 18 milliamps. Step 5. R Thevenin equals V test divided by I test equals 1V divided by 7 over 18 MA equals 18 over 7 kiloohms, approximately 2.57 kiloohms. So the Thevenin equivalent is an 8-volt source in series with 2.57 kiloohms. Yes, this method is more involved, but it's the only way to handle dependent sources correctly. Let's recap everything. Thevenin's theorem says any linear circuit can be reduced to a voltage source and a resistor. The algorithm for V Thevenin: 1. Identify the terminals. 2. Remove the load. 3. Calculate open circuit voltage VOC. 4. V Thevenin equals VOC. For R Thevenin, no dependent sources. 1. Remove the load. 2. Kill all independent sources. 3. Calculate equivalent resistance. 4. R Thevenin equals Rec. For R Thevenin with dependent sources: 1. Remove the load. 2. Kill independent sources only. 3. Apply test source 1V or 1A. 4. Find resulting I or V. 5. R Thevenin equals V divided by I. Here are some pro tips from years of teaching this. Tip 1. Always double-check the polarity of V Thevenin. Draw the positive terminal clearly. Tip 2. R Thevenin should always be positive. If you get a negative resistance, you made a mistake. Go back and check your work. Tip 3. When in doubt, use superposition to find VOC. It always works. Tip 4. For Thevenin, you can also use the formula Thevenin equals VOC divided by ISC, where ISC is the short circuit current. Sometimes this is easier than the test source method. Tip 5. In the real world, you can measure the Thevenin parameters. Measure VOC with a voltmeter. Measure ISC with an ammeter. Calculate Thevenin equals VOC divided by ISC. Engineers do this to characterize unknown circuits. I've left a practice problem on the screen. Here's a circuit with multiple sources and resistors. Find the Thevenin equivalent as seen from terminals A and B. Then calculate the current through a 5 kilo ohm load. Pause the video. Work it out. The complete solution is in the description below. Here's the truth. Thevenin's theorem is one of those rare topics that, once you truly understand it, changes how you see circuits forever. You stop seeing complexity. You see equivalence. You see simplicity. Master this theorem and no circuit will ever intimidate you again. Thank you for watching. Now go solve some circuits.